Hey there, my name is Julien Serrail. I'm the CEO and co-founder of UBIK. UBIK Agents aim at creating the AI operating system in order to allow any companies integrate AI agents at scale without the burden of the technicalities of developing an AI project. In this video, I'm trying to explain the different concepts about a RAG system, how to build a multimodal, multi-vector one, and try to go deep into what could be the enhancement that someone could try to implement in its RAG pipeline. If you want to use UBIK RAG pipeline, you can go to our website, create an account, and start building on top of that. You can go to ubik-agents.com and start building on your own. I wish you a good video and hope that you'll enjoy. Large language models have a fundamental problem. They hallucinate by design. They can confidently present incorrect information. RAG, Retrieval-Augmented Generation, directly addresses this challenge by grounding AI responses in verified information sources. RAG integrates two components. First, a retrieval system that fetches relevant documents from your knowledge base. Then, in the second step, a generation system that produces responses based specifically on those documents. The architecture prevents hallucinations, overcome knowledge cutoffs, and enable customization with proprietary data. Organizations implement RAG to create AI systems that answer questions using only their specific documentation, policies, or knowledge bases. The technology powers customer support systems that reference product manuals, research assistants that cite scientific papers, and enterprise search tools that retrieve company-specific information. File parsing is also an important challenge when building a RAG pipeline. In fact, file parsing solves a fundamental RAG challenge, converting diverse content formats into machine-processable data while preserving their meaningful structure. Parsing extends beyond text documents to multiple modalities. Modern RAG pipelines process text documents, PDF, Word files, HTML, audio files, using speech recognition models like Whisper, image and video through vision language models, and structured data from databases and APIs. Each modality requires specialized preprocessing. Audio needs transcription, images need visual feature extraction, and videos require frame analysis and temporal understanding. Tools addressing this challenge include PyPDF2 for PDFs, ApacheTK for multiple formats, Whisper for audio transcription, and vision language models for image understanding. Their effectiveness directly impacts your entire RAG pipeline. Poorly parsed content creates irretrievable information. Machines cannot understand content directly. Embedding models solve this fundamental challenge by converting information into numerical vectors that capture semantic meaning. Modern embedding models serve different purposes. Some of them are text-focused, like Qwen3 embedding, Modern BERT, or OpenAI embeddings. Others are multimodal, clip models, image bind, or for example, document screenshot embedding. Some of them are multilingual, specialized for cross-language understanding, like ME5, for example. Or others are domain-specific models, optimized for legal, medical, or financial content. These models transform content into points in high-dimensional space, where similar meanings cluster together, with new growth and increasing sales appear close to each other, while unrelated concepts remain distant, allowing machines to comprehend relationships. The quality of these embeddings directly determines your RAG system retrieval precision. Weaker embeddings fail to capture nuance distinctions, while strong embeddings accurately identify relevant information, even when expressed differently. Information retrieval faces a persistent challenge. Users often search for concepts using different terminology than documents use. AI-powered search addresses this semantic gap. Traditional search algorithms like TF-IDF and BM25 match keywords effectively, but fail with synonyms, paraphrases, or conceptual relationships. They find global warming when you search for exactly those words, but might miss documents about climate change or greenhouse effect. Vector-based semantic search overcomes this limitation by comparing meaning rather than exact terminology. Using embedding models, it transforms queries and documents into vectors and measures their similarity through metrics like cosine distance or dot product. This approach enables finding documents conceptually relevant to your query, even without terminology overlap. A search for natural language processing application can retrieve documents about practical uses of NLP or implementing language AI based on semantic similarity. Storing and retrieving millions of embedding vectors efficiently presents a significant technical challenge. Vector databases solve this problem with specialized architecture designed for similarity search. Vectors in RAG systems are simply arrays of floating point numbers, typically hundreds or thousands of values representing content semantics. Traditional databases excel at finding exact matches but struggle with similarity searches across high-dimensional vectors. Vector databases like Pinecone, UBIK Quadrant, and Milvus optimize for exactly this use case. They store three key components: the vector themselves, metadata about the source content, and specialized indices that enable rapid similarity search at scale. The performance difference is substantial. Querying millions of vectors in a traditional database might take seconds or minutes, while vector databases can return results in milliseconds. This efficiency enables real-time RAG application that will otherwise be prohibitively slow. Searching through millions of high-dimensional vectors presents a computational challenge. Finding the exact nearest neighbors requires comparing a query against every vector, computationally infeasible for production systems. Approximate nearest neighbor (ANN) algorithms solve this by trading perfect accuracy for dramatic speed improvements. Rather than finding the absolute closest matches, they identify vectors that are very likely amongst the closest. Often within 95% accuracy, but order of magnitude faster. Key ANN implementation include HNSW, hierarchical navigable small word, creates navigational shortcuts between vectors, IVF, inverted file index, group vectors into cluster to narrow search space, PQ, product quantization, compresses vector to reduce memory requirements. These algorithms are what enables vector search to scale efficiently to millions of documents, while maintaining millisecond query times. Without them, similarity search would be prohibitively expensive for all but the smallest document collections. Each algorithms offer different trade-offs between index build time, query speed, memory usage, and retrieval accuracy. For RAG systems, slight accuracy reductions are often acceptable when balanced against substantial latency improvements. Initial vector retrieval prioritizes speed, but often sacrifices precision. Re-ranking addresses this challenge by applying more computationally intensive models to refine a small set of initially retrieved documents. Re-ranking can be implemented through 1. Dedicated re-ranking models like Query Ranker or BG Re-ranker specifically trained for this task. LLMs directly using their activation score to determine relevance, or hybrid approaches combining multiple signals at the same time. LLM-based re-ranking is particularly powerful as it can filter content based on usefulness for the specific question, not just relevance. This reduces the volume of text sent to the final generation step, improving both quality and efficiency. This two-stage approach works because vector search quickly identifies 20 to 50 potentially relevant documents from millions, while re-ranking precisely evaluates just these candidates with more sophisticated models. Different embedding models capture different aspects of content. Multi-vector approaches address this by encoding the same content through multiple distinct embedding models, capturing complementary signals. Unlike simple vector, true multi-vector representation maintains multiple vectors for identical content, each created by a different embedding model. For example, dense embeddings capture semantic meaning, sparse embedding excel at keyword matching, domain-specific embeddings recognize field-specific concepts, cross-lingual embeddings bridge language barriers, and multimodal embedding models allow to encode a screenshot, for example. This creates a more complete representation of content. For example, a medical document might have one vector optimized for general concepts, another for medical terminology, and the third for patient-friendly language. During retrieval, these diverse representations allow matching content through whichever embedding best captures the query's intent. A technical query matches through the specialized embedding, while a layperson query finds the same content through its general representation. This approach significantly increases retrieval robustness, particularly for content that might be described in multiple ways or accessed by users with varying levels of domain knowledge. Both keyword and semantic search have inherent limitations. Keyword search misses conceptually similar content using different terminology, while semantic search might overlook exact terminology matches. Hybrid search addresses this challenge by combining multiple retrieval methods in parallel at the same time. The most common implementation combines BM25, which is keyword matching, with vector search. This approach excels at queries that benefit from both exact matching and conceptual similarity, like technical documentation searches that include specific terms alongside broader concepts. In order to implement it, you need to execute in parallel the searches using the different methods before normalizing their score across the different algorithms, and then determining optimal weightings and applying either weighted averaging or fusion techniques. The engineering complexity is substantial, requiring expertise in both traditional information retrieval and vector-based approaches. The performance improvement can be substantial, often between 15 to 30% better than either method alone, particularly for domains with specialized terminology or queries that mix specific terms with conceptual elements. Standard embedding models compress entire text chunks into single vectors, which obscures the contribution of individual words. Late interaction models like Colbert or Colpally fundamentally transform this approach. This model generates separate embeddings for each token, essentially each word or subword in both queries and documents. This token-level representation preserves the distinct meaning of every word rather than blending them together. When you search for protein folding algorithms in molecular biology, each term maintains its own distinct representation. The critical advantage is precision. Late interaction models can identify exactly which words in your query match which words in a document. This enables the system to explain why a document was retrieved, perhaps because protein folding appeared in one paragraph, while algorithms appear nearby. Traditional models might miss this fine-grained connection because they average everything into a single vector. Colpally extends this precision to visual content, creating embeddings for individual image patches that can match directly with query terms. A diagram labeled protein structure can be matched specifically with those terms in your query. This granular understanding comes with computational cost, but delivers superior precision for domains like medical, legal, or scientific research, where exact matching of concept is essential. Thanks for watching the video. I hope that you enjoyed it and that you got a lot of information about our RAG system at UBIK. If you want to create an account, you can go on our website, ubik-agents.com, in order to create your account and start using our RAG pipeline. If you like the video, feel free to drop a like, a comment. I'll try to answer to as many remaining questions you might have at the end of this video. And also subscribe to the channel, because we will try to produce more content about the AI operating system. It was Julien Sehaille, CEO and co-founder of UBIK, and I hope to see you soon on the channel. See you!